Woohoo! Welcome back. Today we're going to be talking about 1.3 linear functions. Most of what we're going to be doing in terms of math will be a review from whatever algebra class you might have taken before this. Just in case you don't remember it, I have included some of those algebra lectures in the playlist and in Canvas. And so what we're gonna talk about here will just be some reminders. It won't be a full lesson on the algebra. So again, if you're feeling a little bit wobbly about how to graph lines, please ask me, ask the tutors, check out some of those review videos and make sure that you're feeling really confident about lines, because what we're gonna do is we're gonna take what you know about lines and add in finance. Woohoo! Yay, money. Okay, I've got Godzilla here to help me explain all of this, and I'm just going to go over a couple of key concepts. So the first thing we're going to talk about is slope. Almost all lines have slopes. Every now and again you'll come across a line that does not have a slope because it's vertical, and so the slope is complicated. If it's straight up and down, then we have an undefined slope. But all other lines will have a slope. And one way to talk about it is to describe it. So slope, which in shorthand a lot of times is, we use m for slope, and that is basically is a measure of the steepness, there we go, of a line. Okay, so what the heck does that mean? Well, we've got a couple different ways we can look at lines. If I were to just sketch a line right there, I could talk about which direction it's headed. Like, it is headed from down here to the left up and to the right. And in mathematics, we would say the way that this line is oriented, the slope is positive. So I could say the slope is greater than 0. And I could have a flat slope. If it's perfectly flat, that means the slope is 0. And if our line is pointed downwards, and I know this is confusing because we got arrows on both sides, and yet I'm saying that it's pointed downwards, but we always read lines moving. Graphs are always read from left to right, so we're heading in that direction, from the L to the other side. The same way that we read. Woohoo! We read from left to right. We read lines from left to right. So, as this one is headed from up here down, we consider this slope to be negative. The slope is less than 0. And so what we could talk about is, I could say if I have, let's see, if I had two lines and one was really steep like this and one was a lot flatter like this, I would say that this slope is greater than this slope. So we can actually look at comparisons of two lines. So if this line has slope m1 and this line has slope m2, then m1 is greater than m2. Okay, so basically slope is just describing kind of where the line is headed, and that's going to be really interesting for us because we're going to use that for forecasting when we're talking about finance and economics. We've got another concept, which is a lot of people refer to as the mx plus b form of a line. This is called the slope intercept form of a line. That's this guy. It's called slope intercept. Why is it called the slope intercept? Well, if we've got y equals mx plus b, any linear equation can be put into this format as long as it has a y and an x. So as long as there's a y and an x, doesn't matter where they start out, doesn't matter what numbers are involved, we can rewrite it like this as long as it's a linear equation. So if you solve for y, then you're guaranteed that whatever number ends up in front of x, that's the slope. And we're also guaranteed that whatever number is off by itself, the constant, this is going to be the intercept. This is the intercept when x equals 0. So this is the y-intercept. And as I said, I'm hoping that as I said all of those things, that you were like, oh, that's right, I remember all of this. If you're thinking, oh my goodness, this is really a little bit hazy, or maybe you don't even remember this at all, you may want to take a break. And again, ask me, ask the teacher, ask the tutors, go check out some of those review lectures, really remind yourself how to work with lines, and then come on back. I promise if you pause this video, we will be here waiting for you. You can go now. It's okay. Really, you can go. Okay? Awesome. Okay, welcome back to everyone who paused the video there. Let's go ahead and do a problem. Woohoo! The problem here says that we should find an equation of the line that passes through 2, 3, and 4, negative 6. So the first thing I'm going to do is, I don't have grid paper right here, but I'm going to go ahead and just sketch out where these 2 points would be. So 2, 3, remember that our ordered pairs are always written in the same order, x, y, when we're in 2 variables. And so the x value is going to be 2, the y value is going to be 3, so 2, 3 is somewhere like that. And then 4, negative 6, that's going to be, x is going to be out at 4, but y is going to be down here. And this is just a sketch. This is, obviously there's no grid, so I'm just kind of eyeballing what I think it looks like. So the first question is, how many lines pass through those 2 points? And the answer is, it's just a single line. The line that passes through these 2 points and continues on, there's just one of them. And so we can find the equation of that line. If you have 2 points, you've got a line. Or if you've got 1 point and a slope, you've also got the line. So we're going to be dealing with the 2 points version. So how do we get the equation of this line? I mean, I could look at it and say, well, by everything we talked about up here, this seems to be headed downwards, right? When we read left to right, this seems to be headed down. So the slope is negative. I can see that I have an x-intercept right there. I can guess that somewhere up here I have a y-intercept. It seems like it's headed for the y-axis. So I can guess that I should be able to find all these interesting values, but how do I actually go about doing it? Well, there are a couple ways to do it. This is what I would recommend. Almost always, whenever you're dealing with lines, find the slope. If you're not given the slope, or the slope isn't otherwise obvious, find it. Now, how do we do that? Well, we've got a formula for the slope. And you might remember that the slope is the rise over the run. y1 minus y2 over x1 minus x2, or y2 minus y1 over x2 minus x1. It's taught in different ways. Basically, what's important to remember is that the y's go on top and the x's go on the bottom. So that's the rise is how far up and down. That's the y's. Rise, y's, see there? And then run is how far left to right. So that's the difference in the x's. The other important thing to look at is that it's really important to make sure that whichever one you start with on top, you also start with in the denominator. So y1 starts, so x1 starts. y2 starts, x2 starts. So in our case, I have to pick one of the y's and one of the x's. And let me go ahead. I'm going to color code this. 2, 3 will be this point. Just so we can keep track of the difference, so you can kind of watch how everything interacts. There we go. 4, 6 is down there. So I have to pick one of the y values. I'm going to go ahead and pick 3. And I'm going to subtract the other y value, which is -6. Now 3 comes from the blue point, so I'm going to make a note of that here. And the -6 comes from the yellow. Now, since I started with the blue point on top, I have to start with the blue X down on the bottom and then finish up with the yellow X down on the bottom. So let's see, the blue X was 2 minus, and then the yellow X is 4. See how I did that? I found the difference in the Y's and the difference in the X's. And 2 and 3 go together. 4 and -6 go together. Okay, so up on top, I get 3 plus 6. Down the bottom, I've got 2 minus 4, that's -2. So 9 over -2, so I've got -9 halves. Woohoo! So, does this agree with what we already know? Abso-stinkin-lutely. We said this was decreasing, it was going down, so it should be a negative slope, which we got right there. Now, something that people often ask, and I often answer. In fact, I'm going to answer this time. Can I work out the slope the other way? Absolutely. You do not have to pick one way or the other. So in other words, this time I'm going to start with the yellow values, and then I'm going to subtract the blue values. Woohoo. Okay, so the yellow, remember the rise or the y's go on top. That's -6 minus 3. So I've reversed the order here. And then the yellow X is 4. And the blue X is 2. So up on top, -6 minus 3, -9. Bottom numbers, 4 minus 2 is, look at that. I get the same slope regardless of which one I start with, the blue one or the yellow one. So you get that freedom, but you got to figure out what the slope is. Now, on our graph, what the heck is the slope? Because you're not going to see -9 and 2 on the graph. Or are you? Dun, dun, dun! If you had I don't know how to say it. Back in the olden days of the 90s, before cell phones, so we had nothing better to do. Everyone spent basically 18 to 20 hours a day doing math. There was nothing else to do. Every now and again, someone would yell hammer time and we'd all dance, do, 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 But then the rest of the time we were all doing math. So we did a lot of math because there no cell phone. There was no Candy Crush. There was Pokemon, but it was, cards, and it was really different. So, okay, so we're doing math all the time, and so we learned to calculate slope slightly differently. The way you can calculate the slope from the graph is you can actually look at, here's the run, and here is the rise. Now, in this case, since this value is falling, it's negative, right? It doesn't really rise. It's more of a fall. So if we look at this distance here, all the way from 3 down to -6, we see that this is 9. So it's going down by 9. And the run, how far it goes across, from 2 to 4, this is 2. So you can also see -9 halves. There's the 9, it fell, so -9, and there's the run is 2. Okay, so we've got that. Yay, we've got a slope. So now that we've got the slope, what do we do? Because we don't have an equation yet. And the answer is, for a lot of people, you go ahead and use the slope-intercept form to find the equation. Now, are there other ways to do this? Absolutely. There are a bunch of ways to come up with the equation of a line, but we're going to use this one primarily because I'm guessing this is the one you're most familiar with. And if you're ever curious, if you want to come to office hours, say, please give me more math. And I'll say, oh my gosh, I've got so much math here. Because again, I lived through the 90s, no cell phones. All we did was math. We got tons of math. So I got I got boxes of math I can give you. But this, we're just going to be using the slope-intercept form. If you're curious, there are other forms. There's point slope form, which you might be familiar with. There's standard or general form. There are a lot of forms. It's awesome. Lots of lines. But we're going to use this one. And we already know that the slope is -9/2. So we know y equals -9/2 x plus b. We do not know b. B is the y-intercept. We don't know what that is. That is whatever the point is up here where this line would intersect the y-axis. So we got to figure that out. How do we do that? Well, we pick a point. You get to choose which one you want. I'm going to choose 2, 3. Because of the 2 points, it seems like it's the easier one. I'm just being, I'm just being a little lazy. This one has a negative and the numbers are bigger. I'm like, don't want to do that one. I'm going to use this one. So what we're going to do is plug it in. So I have y equals -9/2 x plus b, and I plug in 2, 3. So the y value is 3. The x value is 2. And we have to figure out what b is. We also need to get some more paper. So let me continue this on another sheet of paper. So we've got 3 equals -9/2 times 2 plus b. We need to figure out what b is. Okay. This doesn't seem as hard as it could be. I mean, it's not my favorite thing in the world, because there is a fraction, but let me grab my red pen of destiny. The really great thing about this is, maybe I'll rewrite it. I know fractions can be a little bit intimidating some of the time. If you rewrite the whole number 2 as 2 over 1, then we see, wait a minute, this is multiplication. So the 2's, top and bottom, cancel out. Woohoo! Life is good. So 3 equals -9 times 1 plus b. So 3 equals -9 plus b. Oh my goodness, we could almost do this without solving it. But let's solve it anyway. We could do it in our heads too, possibly. B equals 12. Yay! So what does that mean? Well, that means that my graph was wildly out of scale. But basically, that means that the point b equals 12 is way up here at 12. Right there is the y-intercept. So when x equals 0, y equals 12. So how do we use this? Well, we had y equals -9/2 x plus, and then that number is going to be 12. Yay! Now, how could you check this? Well, you could graph it, double check that it matches this graph, or you could plug in this value. Do you get 4, -6? If you plug in 4 here, do you get -6? I don't know. You should check that. I'm leaving it as an example for the student. Ooh, that's another thing we had in the 90s. Books didn't work things out. They said this is left as an example for the student. The 90s were so much fun. Awesome, really. Okay, so Next question. Do you want to do some more math? And the answer is, of course you do. So we're breathing deeply, even though all of a sudden you're like, oh no, oh no, oh no. There's a lot of words on the paper, on the screen. We can do this. Godzilla's here. Rate of change. Now, you've probably noticed, if you've already taken some economics classes, that if there's one thing that an economist loves, it's jargon. Jargon is awesome. So in economics and in some of your other classes, you're going to see, instead of rate of change, you're going to see the word rock. Isn't that rocks? Isn't that awesome? So this measure tells you how fast something is changing and in what direction it is changing. So the rate of change is the total change divided by the amount of time that has passed. Wait a minute, that's a fraction. That's a fraction that's talking about change. What's change? Change is the difference. Wait a minute. Wait a minute. That sounds like the rise over the run. Oh my goodness. It's our friend, the slope. Now, is it always the slope? No. It is the slope when we're talking, and I know this looks hideous. It's like decimals and all these things running around. So, it is the slope when you have a line. Now, what is the rate of change if you don't have a line? Well, that's what we're going to do later on when we start talking about derivatives. Things get a little more interesting when we're not talking about lines. So we're going to start off talking about lines. It makes it easier. So, our example, the gross domestic product, the U.S. gross domestic product, GDP. Wait, we're about to do some time travel. It's very exciting, which they're going to set as Y. For the years from 2011 and projected to 2021. I know the book is so old. Yes, it is. Because when I'm recording this, 2021 has already passed. And a really great instructor would actually know what the GDP was to be able to confirm whether it actually fits here. Yes, that would be what a great teacher does. It is not what I did, though. So, the rate of change, rise over the run, is the slope. What is my first question going to be? Well, what is the slope of the graph of this function? So, what does that even mean? Well, I've got an equation. Y equals, notice this is a number. Y equals number times x plus number. Wait a minute. That looks just like y equals mx plus b. So how do we know what the slope is? The slope is whatever the number is next to the x. Oh my gosh. The slope is 977.8. And what is that measured in? This is measured in billions of dollars. And now the slope isn't just a single number, though. It's the rise over the run. So it's the total change over the amount of time that has passed. So it's 977.8 billions of dollars per year. Does that make sense? It's 977.8 billions of dollars per year. So, and if no one has ever told you that, I'm going to tell you right now, you ready for your mind to get blown? The word per in math basically means divided by. Percent means divided by 100. Per year means that we're dividing by the time that has passed. So anytime you hear per, it means divided by. Okay. Interpret the slope as a rate of change. So let's go back up here. I know this is a bunch of jargon and a bunch of words, and it's like, ugh. So what the heck is even going on? This measure tells you how fast something is changing and in what direction it is changing. Okay, so where does it say direction? Remember from the first page, if it's going up, it's positive, and if it's coming down, it's negative. This number is positive. So that means that the change in the gross domestic product is positive. So the gross domestic product is increasing. This makes sense. We expect this to happen. We expect economies, generally speaking, since populations continue to expand, we expect the economy to keep expanding. So the fact that GDP is going up is great. We do not want it to go down. Down is bad. Up is good in this particular case. So this is awesome. So in other words, we've got the fact that the GDP is increasing by, or the GDP is expected to increase it's another way we could phrase it. 977.8 billion per year. So that means, oh, and hopefully you know these little ditto marks, like quotations, mean copy whatever was above. So the GDP is either increasing by or is expected to increase by, depending on your perspective, right? This is a forecast. When this was written, billions and billions of years ago. This book, I believe, was out floating in space before the Earth even came together. I mean, an abomination like this doesn't just get written. This book probably existed for beyond time. I mean, really, this is one of the eldritch terrors, I think, is this particular book. But so when they wrote this, they were forecasting. So you might want to use the expected to increase by. So what does this mean? This means that if we know our GDP this year, then we could guess next year's GDP by taking this year's GDP and adding 977.8. But what if we want to know 2 years from now? Well, then if we wanted to know 2 years from now, this would be, we would take 977.8 times 2, because it's per year. If we want to know 3 years from now, we would take it and multiply by 3. Woohoo! Yay! So, now, one thing that I'm going to struggle with a little bit, because this is just my desktop, and I don't have access to a good way to show you Desmos tonight. Graph this function using Desmos. So I'm going to leave that for you. And definitely graph this and take a look at what it looks like. It's an interesting little, it's a graph that increases. What should the domain be? That is the interesting question I want to answer right now. So unfortunately, you're not here. If we were in class, I'd be asking and everyone would be like, oh, I wonder. So let's take a look at what the rules were. This is the U.S. gross domestic product, Y, for the years from 2011 and projected to 2021 is given by this. So what should the domain be? I would think the domain for this would be from 2011 to 2021. Does that make sense? Woohoo! Yes. So now, what are the X values? And this is where things get a little weird. I went over this pretty quickly when I didn't actually even read it because I didn't want you to worry about it then. But now we got to think about this. Does that mean that 2011 is X and then 2021 is X? And the answer is nope. X is the number of years past 1990. So what does that even mean? Well, that means that if the year is 1990, X would be 0. And if the year is 2011, X would be 21. Because 2011 is 21 years past 1990. And if the year is 2021, what's X? Weirdly enough, 31. So that means that the domain, it's a really weird interval. It's the interval from X equals 21 to X equals 31. And so we can take a moment and talk about what is even happening with this. Well, when you're coming up with equations, you're using a lot of different data points. And you're trying to get the data to fit a line. Now, does the data fit the line exactly? No, I can guarantee you it doesn't. If we actually looked at what the GDPs were for from 1990 to 2021, it would be dots, and they bounce around a lot. And you're trying to find a good line that fits the middle of them. So that's what this line is. However, when you're actually trying to figure out what this line would be, sometimes you have to take into account numbers like 1990. So that's why they set X equal to 0 in 1990. Did they tell us why? No, we just take it as it is given. That's the way they fit it together. This part is frustrating and can be a little confusing, so please ask me more questions. You're welcome to ask the tutors. They will not know a lot more than I do, but they might say it in a less confusing way. So, definitely talk to tutors, talk to me. What did I do? Well, my solution for this was to come up with a far simpler example. So for my example, I'm going to look at leaves. Given the following values, determine the rate of change. Okay, so rate of change, otherwise known as the slope for us right now. Let X represent the number of days that have passed. Okay. And Y represents the number of leaves on the ground. So I've simplified it a lot. I'm not giving you a lot of details. But basically, I say 2, 10, and 14, 249. So what does this mean? After 2 days, there are 10 leaves on the ground. Oh no, I've run out of room. There we go. And then, so that's the first, so let's call that the green. That's the green one. That's this one. And then 14,249. Anyone who's ever had to rake leaves knows that this happens. After 14 days, there are 249 leaves on the ground. So what's happening? I'm sorry, I ran out of room again. Well, I will tell you, if it wasn't clear, I came up with this idea in the fall. I was watching leaves fall from the trees. And so what happens is, in the beginning of fall, just a few leaves have fallen, but then suddenly all of the leaves go out of the tree and they fall on the ground. And so let's take a look at the rate of change. So the rate of change, ROC, is the slope, which is the rise over the run, which is the y2 minus y1 all over x2 minus x1. I'm going to go ahead and choose the purple guys first. So 249 minus 10 all over x2 minus x1, that's 14 minus 2, so the difference in the y's over the difference in the x's. That's 239 over 12. And through the magic of television, that's approximately 19.92, I believe. We can double check it. Can you see that? Yeah. 239 divided by 12. I hope it's, yeah, it's 19.916666, etc. So it's approximately 19.92. And I didn't tell you how to round it. So all you can do is give your best guess. So, you know, it's one of these two. This is the rate of change. And then what are the units? So what are we measuring on top? The top, the 249 and 10, that's the Y. That's the leaves per. And what is X? X is the number of days. So in other words, what we are guessing as that every day, another 20 or so, approximately 20 more leaves fall on the ground. Leaves are falling at a rate of about 20 per day. Do you think it's a good way to measure this? Now, this is going to depend on whether or not you've ever been in a position to watch how leaves fall out of trees. Do they fall at an even rate? So as you watch a tree, can you watch leaves slowly fall and just fall, and then they fall one at a time? They keep falling all day and all night? And the answer is no, that's not what happens. When fall happens, what'll happen is no leaves will fall out of the trees, and then suddenly there'll be wind and a bunch of leaves will fall. And then it could be 2 or 3 days, and then maybe it rains and a bunch more leaves fall. So some days, maybe no leaves fall. Other days, a bunch of leaves fall. So what does it mean that I'm saying it's about 20 per day? So this is an average. A rate of change is a speed, but it's not ever going to match what's really happening. It's an approximation, and it's an average. So do I think this is a good measure? It's not a great way to measure it, because it misses, like, is it possible that all the leaves fall out of the tree on one day? Absolutely. So are we measuring all the details? No. What are we getting? We're getting an average, which allows us, like we did up here, to say, well, more or less, we're expecting that GDP is increasing. So the GDP is going up by what? About 977.8 billion, or close to $1 trillion a year. So each year we're adding $1 trillion to the GDP. Does that mean it happens that way exactly each year? No, every year is different. Some years there's big productivity. Some years there's, there might be a shutdown. There may be a pandemic that slows things down. Can we forecast this? No, I don't think anyone was expecting it would happen in 2020. So that was not what was being expected. This was just our forecast, our guess. Same thing here. This will give us a guess. So this is what we're aiming for. For the rest of the semester, we're going to be doing a lot of math that's very concrete. You know, I give you a formula, you work it out. However, the formula is going to give us a number, which will be a guess. It will be a forecast for what we expect to happen. We'll say the line is heading in this direction. Does that mean it always goes exactly that direction? No, it might be a little bit higher, a little bit lower, but it gives us a place to start. So that's what our goal is, to give you a way to come up with a way of guessing or forecasting what's going to happen in the future. Woohoo. Okay, you guys made it through how long was that? That was really long. Almost 40 minutes. Oh my gosh. Very long lecture. You are awesome. Go get yourselves something to drink. Get out, get some fresh air if you can, some exercise, do some art, do some music, watch some TV, whatever it is. Relax your eyes, relax your body, kiss your brain, and congratulate yourself for making it through some really dense stuff. Next up, we get to talk about money and supply and demand, which is one of my favorite things in the whole world. So I'm very excited. And so until